Well, thanks for the introduction. And today I'm honored to introduce our work, TRACI Network Acceleration of Input Dynamic Communication for Large-Scale Deep Learning Recommendation Model. So we have seen the prevalence of recommender system in many applications, like search engine, e-commerce, and social network. At the same time, we also see the success of deep learning, the use of deep learning in many tasks. So, which motivated us to use deep learning recommendation model as a recommender. And here's the outline of today's presentation. And first, we'll see the DRM algorithm and its systems. So firstly, for the DRM models, the input queries will send into two parts. In the left part, it targets numerical features, and it will be sending to an MLP layer with about 100,000 parameters. And the right part will be sending to the embedding table, which target categorical features, and typically the embedding layer has huge parameters, about 1 to 100 gigabyte. So after these two operations, there is a feature interaction, and then it will be sent to the top MLP to get the prediction result. So when we look at this DRM model, we find that the embedding layer is the bottleneck, and it has nearly a 99% of the parameters. And this size could add up to 10 terabytes in the SOTA models. So for the embedding table, there's an example. For the input query, it may get some dynamically changing index. So it will look up the table with index 0 to N7. Do the table lookup, and then it get the response, and do the reduce operation, for example, sum, and get the output. So this work mainly focuses on the distributed GPU system for the DRM, because GPU system typically offer high network bandwidth and high capacity of memory. So the embedding table is partitioned and scattered across GPUs. And for example, input 0, look at the table in GPU 0 and GPU 3, and this will lead to the request and response, which is noted as network traffic. So we could use this kind of description to annotate this operation, like output equals to aggregation of E0 and E3, which means the output is the aggregation equals to the aggregation of the query responses. And in a similar way, we could describe the other operations. So since we have seen the DRM algorithm and DRM systems, we want to do some profiling to see where's the bottleneck. And we do the end-to-end performance modeling and evaluation, and we found that in typically A100 systems, about 43% to 53% time is consumed in the communication part. And when we improve the computational performance or decrease the communication performance, this proportion will increase dramatically. So this work aims to elevate the communication bottleneck of the embedding layer. So let's walk through our idea with a comparison of OREDUCE and the aggregate operation used in DRM. In OREDUCE, each GPU sends data to every other GPUs, and this is a uniform operation. But in the aggregate operation in DRM, the input query will ask for different number or different size of the response, and this pattern is dynamical. So the left part has been optimized with some specialized network architecture, like NVIDIA Sharp, and this communication pattern is static. But for the right part, we haven't seen any network acceleration opportunity by now, and this is a dynamic communication pattern. So here we want to show how to find an optimization opportunity for this aggregate operation. And in the left above part, we show that the one response was sent to all these GPUs. And in the bottom part, we show that in the aggregate operation, this data just sent to 3 of them. And we'll show this process one by one. In the traffic, without optimization, GPU 0 send the response to GPU 1, then GPU 0 send it to GPU 2. Then finally, it's sent to GPU 3. It's sent one by one. And similarly, in the aggregate operation, it also needs the one-by-one communication. But we'll see that with communication optimization, maybe we have some opportunities to reduce the data transmission, like GPU 0 send data to GPU 1. And if we could store the data in the leaf switch 1, and it could just send the same data from leaf switch 1 to GPU 2 directly, and then send the data from leaf switch 2 to GPU 3. So similarly, we could do the operation for the aggregate operation. So we found that there is input reuse by the multicast in the reduce, and in this pattern, we always send it to all peers. So we want to exploit the input reuse based on this dynamic access pattern, and we'll show how to do it now. So in this part, in the same example, GPU 1 send a request to GPU 0, and GPU 0 send a response to GPU 1. And if we just store the data in the leaf switch 1, and when next time GPU 2 send request to GPU 0, and it just goes through this leaf switch 1, it will get the data. There's a cache hit, so it could directly send data back. So this is a basic idea of exploit the input reuse. So in this slide, we'll show how to utilize the output reuse. And here, one request could ask for multiple responses in reduce and aggregate operation. And in this pattern, we also need to send data one by one without optimization, like GPU 1 send data to GPU 0, and then 2 to 0, 3 to 0. Also similarly for aggregate operation. But with optimizations, we could do the aggregation operation in the leaf switch 2 firstly, and then to the leaf switch 1, and finally to GPU 0. By this way, we could reduce the redundant data transmission. And similarly, for the aggregate operation, we could do the similar operation, like do the aggregation operation in the leaf switch 1. So we want to exploit the output reuse by in-switch reduction when the output address is the same. And we want to exploit the output reuse based on this dynamic access pattern, especially for aggregate. And here we'll show the basic idea. And GPU 0 send request to GPU 1, GPU 2. And if GPU 2 send the data back to the leaf switch 1, and GPU 1 also send the response, and they could do the aggregation operation when the output address match. And then we send the aggregated result back. So here's the inspiration and how we could find opportunities. So here we show the performance profiling result of the theoretical traffic reduction by use these two methods. And we could find that for these three data sets, the data communication size could be dramatically reduced. And it is note that for this data set terabyte, there is no output reuse because each input query only asks for one output. So here is the detailed implementation. And in the switch part, we add the new reduction table and in switch cache, also CIU cache input unit in the switch. And here's the, initially, there's invalid state in the table. And when there's an incoming data packet fleet with address X, we will register the data with this kind of format. We will store the address and data as the incomplete state. And when we got all the incoming request packet with address X, and we could change the state into complete. And then if there's an incoming request packet also with address X, there's a cache hit. And we could just create the data packet from cache entry 0 and send it to CIU for the later processing. So this is how we could utilize this input reuse. And there's another case that if we just register the address Y with the incomplete state, and there is also an incoming request packet with address Y, there's a cache hit, but this is the incomplete cache line. So in this state, we should store this request in IU and retry next cycle until we make the state change to a complete state. So here we show how we utilize the output reuse by reduction table. And in reduction table, we also register the data by address data and waiting number and arrived number. So if there's an incoming request packet with output address equals to X, we will add the waiting number. And then another request packet come, we will increase the waiting number to 2. So when there's an incoming data packet, we could match the address, and then we will record the data, and we will decrease the waiting number and increase the arrived number. And by this way, we could just drop this packet and not forward it to the next stop until all the data is reduced. So in the next step, another data packet come with the same address, and we will also decrease the waiting number and add the arrived number. And we could find that there's no packet needs waiting, so we could just create a packet and forward it to the next stop. So here's basically the grind. And here we show the experiment methodology. We target the bandwidth with high-speed accelerator interconnect, like 64 gigabytes per second per link. And we test the network topology for a 2-layer fat tree and 3D mesh. And we do the simulation via Gen5 Garnet network simulator. And we do the end-to-end simulation by AstraSim. And we also evaluate benchmarks, including 23 DRM application traces. So this figure shows the communication speedup brought by cache-only method, reduction-only method, and the combination TRACI method. And we could find that across these settings, we could get up to 2.29 speedups. And also for the training embedding communication speedup, these speedups could be even higher, up to 4.92. So this figure shows the influence to the network traffic. The left figure shows that the average number of switch, the response messages were traversed. We could find that by combining these two methods, the average switch hops for each message could be dramatically reduced. And for the right part, we study the normalized bisectional traffic of the network. We could also find that the traffic is much lower than the scenarios without optimization. So we also evaluate the hardware overhead by adding the reduction table and in-switch cache by cacti. And we could find that there's such low percentage of hardware overhead. So here's the summary. TRACI is a network architecture, especially for protocol and switch design to accelerate the input dynamic communication in distributed DRM. And it is built on top of DL accelerator network like NVLink. So there's two main ideas. The first one that the same input is accessed many times. So we could use in-switch cache to avoid repeatedly injecting the same data into a network and thus improve response latency. And the second point is many messages will be reduced to the same output. So we could use the reduction table to perform reduction in switches to reduce network traffic. And we show the result by up to 2.29 speedups. So thanks for your attention, and I'm happy to take questions.